Okay, so in today's lecture, we're going to do some example about the membrane stress and the hoop stress. So maybe we can remember this equation. So basically we have the hoop stress that we say if we have something cylindrical, all right, what will be the value of the stress in one little element over here? So basically, probably need to figure that the hoop stress will be the same independently of the direction. And I think here you have sigma equal, what is it, PR? Is it T or 2T? I think that one is the T.
It's 2T.
The hoop stress?
Yeah, 2T.
Okay, 2T. And then if we look at the cylinder, so this time we have a cylinder. Okay, let's say we made a cut here at the, how can we do this? Let's say here we made a cut over here, all right? And we from the size of the stresses here on this side over here, all right, along these ones, and this one we'll call the membrane stresses or membrane stress. This one was actually then just PR over T. Okay? Okay, so over here we're going to do one or two examples. We'll see. Okay, so here we're going to build, if you want, a spherical gas tank. All right, so if you do it, if we do a figure, this would be our gas tank. And basically the way it's being done or manufactured, if you want, is that we have two half semi-sphere, and we're going to be welding them together, okay? So we put a weld over there. So since this is a tank, the wall of the sphere over here, all right? So I have the radius R and the thickness T, where R is equal to 9 inches and T is a thickness of a 1/4 inch. Yes, sorry. Let me move the camera, might be easier. Let's see now. Yeah, I might be a bit better. Okay, so let's do, I mean, it's going to be a very direct application. This is not complicated at all. So let's say determine the maximum pressure in the tank So basically, it's a direct application. In this case, what is the type of stresses that would be subjected this, if you want, spherical tank will be hoop stress. So you say using the equation using the group stress. Equation will be sigma equals to P R over 2T. Okay, so maybe we're going to need something else here in this problem to solve it. Okay, so I don't know the property, let's make it up. So you want this tank to be made out of what? Steel? Okay. Yeah, it's fine. I would have selected steel as well. So steel, let's say A34. Okay, so we're going to have to find the properties for this one. Okay, so let's see, I don't have access here. Yeah, I have access. So I think at the beginning of the semester, I provided to you tables with the properties of the material, no? So let's see, I'm going to go to this one here. So share. Or if you have them with you, do you have the table with you? Or by any chance? ME304. Let's see, are they here? Maybe in the course material. Oh, okay. No, you give me a good idea. You show me that they are basically on the canvas, not on the canvas side. So let's do that. Yeah, instead of looking all over the places in my notes. So they were probably on the models, I'm guessing. Yeah, first materials table, the first one. Okay, so perfect. So let's see, aluminum material, steel. About A34. So let's say A36. So for A36, what will be the yield stress? So you see, we can select you to use either the yield stress or the ultimate stress. No. So which one do you want to use? Yield will be safer. Okay. So let's use the yields. So we use the yield. We have A36 will be 36 KSI. Okay. So A36, so that was A34, we use to say our maximum stress that we want to happen will be the yield value, and this one will be 36 KSI. Okay, so basically what does that mean? Here we can just solve now for P. For the pressure, we can say P will be equal to 2 times T, our sigma max, divided by R. Yeah, this camera cannot zoom, I think that's all I can zoom out, let's see. Yeah. If when I run out of the screen because I don't really see all of it. Okay, so maybe you can do the calculation for me, guys. So if you do here, we have T, numerical application, would be equal to T equal to 2 times the thickness is 0.25. The maximum stress we are using is 36 KSI, so 36 10 to the 3. Divided by the radius, which is 9 inches. So if we do this calculation, what do you get for the maximum pressure in PSI? 2000? 2000. Okay. Let's see, I should be able to check. So it's yeah, because it's 9 divided by 4, so 36 divided by 36 is 1 times 2. So we'll do on top. Yeah, correct. We didn't need a calculator, okay? But we need to have the calculator. All right, so 2000 PSI. Now, just by curiosity, okay? Let's say if instead of using the yield value, we're using the ultimate. Let's see what was the value of the ultimate. So the ultimate goes from 36 to 58. So basically it's what? 1/3 extra. So basically it would be about 2,700 now for this maximum pressure. Okay, so that was pretty straightforward. Okay, so we're going to do another example. So, example. All right, so in this case, we have a cylindrical body. Okay, that measures okay, I think from here to here, from my figure is not that clear, but let's say that the length of the cylindrical part is 8 feet, and that the diameter of the spherical part is 30 inches. And that the thickness so this is only for the end caps, a thickness of 5/16 of an inch. So this will be here T 5/16 of an inch. This is fabricated from, so this cylindrical part has a thickness of 3/8 of an inch. Okay, and inside the crank, let's say we have a pressure of 180 psi. Okay, so over here, the only way we have to calculate is, pretty straightforward again, determine the stresses in the above structure instead of body. Okay, so basically we need to differentiate between what? Between the spherical part, no? And the cylindrical part. So if we look at the cylindrical, spherical ends, if you want, over here, what type of stress are we going to have? The hoop stress, correct? Which this one is the one we used before. So it's equal to sigma equal to P times R over 2T. Okay, so here we need to be a little bit careful with the radiuses because like before, when we mentioned about the radius here, what is the radius? The inside or outside? Inside, okay? So when we do here the calculation, we're gonna have, so let's say this will be sigma sub h. So we know P is equal to 180. Now what will be R?
15 minus.
It will be 15 minus 5/16 for R. And then twice times the thickness of 5/16. So can someone please do the calculation here? Anyone?
I got 4,230.
4,230. Yes, sir. Thank you. Okay, so and then we need to look here, let's say at the membrane. So it's going to be straightforward. It's going to be, this one is going to be equal to what? PR. So this will be, sorry. It's going to be crowded, but cylindrical section. This time we know we have to deal with the membrane stress, which will be PR instead of 2T's over T. So, I mean, if we do a calculation, what are we going to get? 180. This time, what will be R?
15 minus 3.
15 minus 3/8. Divided by 3/8, which gives you
20? Yes.
7,020?
Yeah.
All right, thank you. Okay, so this is what is asking this problem, but I'm going to add one more thing. All right, because I think that's, I mean, this is straightforward. I don't have anything with this, but basically, let's say that I'm adding here, and this is generally what happened is that, so consider that above structure is built by welding two hemispheres to a cylinder. Okay, so my question here is, what should you consider on the weld section? So let's say that weld over here. So this is our cylinder. These are the spheres, so the weld will be over here. It's just a common sense. So, Johnny, if you want something, how do you think it will break the world? In shear, does that make sense? Okay. So then my question is: so let's say what must resist shear? Okay, so we look at the hemisphere. Sorry, I will look at the sphere. So, because that's what we're welding, okay? Transfer that section, we did calculate that the maximum good stress will be equal to 4,230. PSI, no? Okay, so if we take now one little element over here, that little square element over here, because we say on the stochastic stresses, the stress will be the same in every single direction, no? Yeah, so we could say what? That this will be what? All the stresses on the third direction will be the hoop stress. All right? So yeah, I mean, I'm just using common sense. So basically, this will mean what? This is what means that the principal stress on every direction here, x and y, u1 will be equal to, sorry, x and y will be equal to the hoop stress, which is 4,230. Okay, which will also be the principal stresses. So this will also be sigma 1, sigma 2 over here. Okay, over here we can say sigma 1 equals sigma 2. Okay, so design considerations. And basically here this is, we have learned how to find all the stresses. So let's say engineers. Base the task of designing structural / if you want mechanical components. Oh yeah. Made of different materials. So here we could have what? We study the two materials to be ductile or brittle materials. That have different failure instead of say criteria, let's say mechanism. Okay, so as a result, it is important to select an upper limit of the stress as well as a margin of safety, which we're going to call here we're going to introduce this concept of safety factor. Okay, so over here, if you remember, we did that curve over here. Always a stress strength curve. Okay, where basically we say this will be here the stress strength curve. This will be the, let's say, the yield. This will be the ultimate. I think we say, what was the name of this area here? Elastic. The one over here. You can either say inelastic or plastic, okay? And so on. Okay, so I think we already talked about this, but in general, what's going to happen to the, so let's see which one I put before. So for ductile materials, so ductile material might be the most complicated here, and it will depend on your design. But let's see, what would be the safer design? To put as our limit of stress to put the yield, no? Which basically will limit over here. In some cases, maybe in order you might want, I mean, it's a reasonable assumption to say that you want to see before failure, you're allowing some deformation, no? Yeah, does that make sense? You're allowing some plastic deformation. So let's say, not very conservative. Let's say if you assume that the maximum stress is going to be the ultimate stress, what are you assuming? Is what I just said. Some plastic deformation. Will occur before failure, no? Okay, but I don't know, when can that be important? Let's say it's a component of a machine that is easily replaceable, and it happens that the weight is critical, no? So if you want to save weight, maybe you can make the structure smaller, but instead of taking the yield, you take the ultimate, no? Okay, and say, okay, you know what? That load, that piece of the structure is not that critical. Let's just save some weight, and instead of using the yield, we can use the ultimate. No? Okay? I mean, it depends on your criteria. The whole thing is that depends on your design criteria. Okay, now let's look for, so this one is a lot easier. For brittle materials. Okay, so for brittle materials, in this case, we don't have much of a choice because, I mean, it's not that much of a difference, but what would be our maximum? I mean, give me an example of brittle materials. Ceramic, perfect. So in a ceramic, do you think there is, what would be the shape of the curve in a ceramic? If I do the stress strain curve. I mean, are you going to see any deformation on a brittle material? It will fail, huh? It will break. So probably the will be a very steep, no? Not much at all stress strain curve. But basically, you could see over here that the yield value probably is close to the ultimate, no? It should almost be no different. Does that make sense or no? Ceramic cannot deform, no? Or very little, like a glass. Either it is intact or you break it. So you could see here, I mean, the two values should be about the same. So we can put this. Okay, so for either case, you might also want to introduce what is known as a safety factor. So I'm running out of paper. Got more over here, but not a lot. So here we go. So now let's look at safety factor. Let's see. Safety factor generally is used specifying some books by the letter S, F, or sometimes by the letter N. So what do you think it is? Great. So basically, okay, allowable. So allowable is going to be either your yield or your ultimate. Is that what you call it? So let's say. Okay. So allowable will be, let's say, your sigma yield or the ultimate in most cases, divided by one by the sigma will be your. Oh, good. So maybe I can specify even something more. Will be the actual stress, but if I'm going to be it already, let me just put this. One probably may be a one over here. Because the principal stress is that important. Why? Because what do we say? These values here alone will be obtained how? How do we obtain these two values here, the yield or the ultimate? Table. Right. From the experiment, from the ASTM, but basically we use it. They take a specimen and they use an ASTM machine and they stretch it, no, in a principal direction, no, or one of the principal axes. So these values are obtained throughout one axis of the element. So we cannot compare just to any X and Y. We need to compare it to the stress, which will also be in one of the longitudinal axes. Yeah, so we put this. Okay, so that's it. It's very simple. Okay, so maybe let's put over here. I mean, I think we have here. So I think we did the figure last time. We're gonna do that one for the understanding. Here, didn't we do the one that has the von Mises, the principal? Oh no, it's on the next page. Here we go. So we did the figure. Can you show me the page? I'm not going to do the same thing. I'm just going to do one of them. So basically, what we're saying is that if we are using the principal stresses, what do we say is that okay, on the principal stresses, we're over here, sigma 1, oh, sorry, sigma 1, sigma 2 if you want here. So basically, sometimes it's epsilon, doesn't matter, just a fraction of the. Basically, if you are inside here, we will discuss it, this will be safe, or you can go, if you are outside, will be not safe, no? Okay, so not safe. So when you apply the n over here, maybe the n, let's say if n is equal to 2, then this box will become what? Yeah, will be twice this one, no? Okay. So this is for the principal stresses. Then for the von Mises, was the one of the ellipse this way. Okay, so again, if you stay within the limits here, will be safe. If you go outside, will be not safe. Again, remember this is related to this figure over here, okay? That we did before. For the Tresca criteria, that one is the more difficult to sketch. I'm not able to do it, so let's see. So here we have a straight line. This will be this way, this way.
What's
Okay.
the X and Y axis for the bond?
It's the same, sigma 1, sigma 2, okay? And here would be same thing of it. We have this, I think here then we have this way, and then this way. Okay. So safe. Not safe. So it would be the Tresca stresses. I mean, you can know the equation, but I think it's always good to look at the figures to have a good representation, okay?
So in the real world, the Tresca stresses are the safest.
Which one?
The Tresca stresses because it has the smallest area. It's based off the inside of the bond pieces.
Correct, but yes, if you want to look at it that way, yes. So depend. I mean, it's a good question. Depends, for example, let's say, why are you manufacturing? Are you manufacturing something that is whatever is going to be used for something that is not bigger? Okay, so whatever you're using, designing a garage door for Okay, you look at the hinges and all that stuff. Obviously, all the safety, so safety is not going to be as critical as if you are designing, let's say, a medical instrument that need to be precise, no? Okay. And also depends on what type of material we are using. I think we already discussed this stuff last time. So, for example, if you use ductile materials or ductile materials, like aluminum or steel, which one is the method, which pellet material generally use? Did we discuss that? I'm pretty sure we did. So for ductile material, which one it is? Oh, so we have it here on the page. So remember, for the ductile materials, we say that in most cases, if we repeat it, it's not a problem. So ductile materials, generally we use the von Mises stresses. Then we say the other type of materials would be the probably mentioned that for composite materials. Oh. Which one did I suggest it? The principal stresses. But then probably here you are, I think I might change or add something from what I did before. So for building materials, I also recommended the principal stresses. But here I'm going to add what I'm using the Tresca stresses for the reason you just gave over here. It's the most critical, no? Yeah. Okay. Okay, so we have 10 minutes. Let me just do a summary of everything we have covered so far in this class. Okay, so far we have done what? What I'm expecting from you to learn from this class so far is what? What do you think is the first thing?
Here and the diagram.
But even before that, that's exactly what I was thinking, but I was going to here maybe reaction, shear. Actually, was an assignment due to them?
Yes. Yeah. 25.
Okay, how did it go?
It was fine.
Was it fine? Okay, good. So maybe after this one, I'll see whatever other your results. We'll do one more, and if it's done properly, we'll stop doing this, no? The whole idea is that you learn it, no? You have 2 chances. This is the 3rd time, no? No more. Okay, next, maybe you need to learn how to calculate the cross-section properties. Which means centroids. Moments of inertia. Then you also should know how to calculate after that, or even before that, which is the difficult part. The loading. I think this is the most difficult part. Now that you have the loading in your local section, what can you find? You can calculate the normal stresses. You can calculate the shear stresses. Okay, after today, you should know how to calculate the hoop. and membrane stresses. Okay, and we also, let's say you should be able to do some basic design using one of the three failure criteria, which are principal stresses, stress stresses, or misses stresses. Okay, so for next week, probably I'm going to give you an assignment that will be not that much because I'll give you separate assignments for this. For the first two, basically, or even the first three. I will give you one that will cover probably all the other ones. Okay. So whatever, what could be the typical one I could give you on the next assignment will be what? Whatever. Let's say you have a pipe. I'm completely making it up, okay? But kind of the same plans that we have, okay? That might be this way, and then you might have another pipe turning this way, whatever you want, okay? Turning that way. All right, and here attached. So it's coming from the ground. Let's say it's a pipe that is transferring whatever gas, propane gas, at a certain pressure, no? Okay? And that for whatever reason, you have some loads being applied on this pipe, no? Okay, so I ask you to calculate what are the stresses on the pipe. So it's the same as the previous assignment, but what's going to happen again? What's going to happen in addition in this one is that you're going to have stresses due to the inside pressure of the gas, no? Going through the pipe that you will have to have. Yeah, does that make sense? Okay, then really everything we are doing now, the next thing will be to do, because it's important in this class, is to do the design of power / transmission shafts. Okay, so for example, a shaft in transmission, you will have what? If we look at very simplified, if you work here on the formula, I guess, or the Baja, what could you have? You can have one gear over here, no? One shaft connected to a gear, and here you have whatever, another one that is connected to the, no? So you know how to transfer the power. So what happens when you do the design of a shaft? How do you attach the gears to the transmission shaft? Anyone? Correct. So there you have on each side you have some keys, no? Correct. To connect this component. So what's going to happen at the location of the keys is going to be some stress concentrations, no? Okay. Then due to the loading and so on, so we need to be able to calculate the stresses for different situations. So second part of the semester probably will be is going to be to do power transmission shaft design for in different gears. And what's going to happen once the gears start moving? What happens that the load is not static anymore, but it becomes cyclic, no? So we're going to have to consider a new failure criteria. That will be the Goodman method. All right, so let's stop over here. One thing, guys, if you can late,